So welcome back. In this lecture, I'm going to talk about projectors, Hermitian Hamiltonians, and also spectral decomposition. And these three things are very important for having a good grasp of the formal aspects of quantum mechanics. So let's get started. So after talking about transformations, we need now to talk about projectors, because a question that occurs if you want to finish this analogy between a Hilbert space and a normal vector space in R3, for instance, how do you project onto subspaces? What do you have to do, right? So for that purpose, I'm going to define a projector. So a projector is any linear operator P which satisfies P2 equals to P. Which means that multiple application of this operator has the same effect as single application. Fair enough, but how we write this? How can you express this operator which projects onto a subspace in terms of bras, in terms of cats? Okay, so let's consider a cat psi. The projector onto this cat psi is given by this expression here. And we realize also that if you apply this twice, if you project twice onto psi, you're going to have, okay, here you apply it once, here you apply it twice. We have said that this is normalized, so the norm of this is going to be 1. And as a consequence, we have then that P2 psi is going to be equal to P psi. So this actually is satisfying this condition that said that multiple application has the same effect as single application. If you want, we did this twice here, once here, twice here. You can go on and on and on, and you see that this holds. Now, in general, this was a very simple example of a projector, but in general, a projector may also include a sum of operators. So we can have something like that. For instance, we can define P going from J to 1 up to R, psi J cat, psi J bra. And this R is what we call projector rank. this upper limit here. And what does this mean? This corresponds, this rank corresponds to the dimension of the subspace onto which we are projecting. And as the name says, a projector projects. A vector onto a subspace. And how does it do? Well, what happens is it's going to remove the components of the vector which cause it to lie outside the subspace. Fair enough. Do you want some example? Very simple and something you may be familiar with. For instance, the matrix operator on R3 defined in this way: 1 0 0 1 0 0 0 0 0. This is a projector because what it does is if you multiply this by a 3D vector, it's going to eliminate its Z components. So what we're going to do now is we're going to talk about a very important type of Hamiltonians, who are the Hermitian Hamiltonians. So what we're going to do now is we're going to talk about a very important type of operators, and in particular Hamiltonians in quantum mechanics, which are the Hermitian Hamiltonians. If you've been around, you have already heard of them, and we're going to start with a definition, and we're going to discuss when we say an operator is Hermitian. So we say that an operator is Hermitian or self-adjoint if it's equal to its Hermitian conjugate. So what we mean is if you have an operator A, and if you have an operator A dagger, which is Hermitian conjugate of A is equal to A dagger. Now, this is a definition which works not always, because actually, if you want to talk about hermiticity in a Hilbert space, many times we need to look at inner products. So if you satisfy this condition, this implies that this inner product here, or psi a phi, is going to be equal to its complex conjugate. And normally what you do is, say, if you want to change your inner product, you would start from this condition or something where you have it modified, and it will lead to that. So for our purposes, this definition is okay, but it is important that you bear this in mind. And a big consequence of Hermitian Hamiltonians is that you can guarantee that the eigenvalues, it's bad this one, are real. So what I'm going to do is I'm going to prove this, and we're going to have a look. And to start with, let's write an eigenvalue equation. So we have an operator. So we're going to prove that if A is Hermitian, its eigenvalues are real. This is what we are aiming for. All right, so let's have a look and let's come up with a proof. To start with, we are going to use an eigenvalue equation. So we're going to say that phi n A phi n is a n psi n, whereby this a here is an operator. I apply this operator to the right, and it gave me then an eigenvalue a n associated with psi n, where this is then an eigenstate or eigenvector in Hilbert space, if you want. Okay, so we want to prove that if A is Hermitian, a n star is equal to A. So we need a n star is equal to a n, because this is what is going to guarantee reality. Correct? Okay, we're going to do that, and we have this eigenvalue equation. Now let's have a look at what happens if we have the Hermitian conjugate, if we have a dagger. So let's calculate what is psi n a dagger psi n. Now we had a definition, and that's why I was telling you this inner product is really important, because if you have psi n a dagger psi n, you know that this is going to be psi n a psi n star, correct? Now we are assuming that A is equal to a dagger, which means that psi n a psi n is going to be equal to psi n a psi n star. But if you look back, you're going to see the following. You are going to see that this guy, if you would like to compute it, you know that psi n a psi n star is going to be equal to a n psi n psi n star. Correct? It has to be, because we have just applied here, if you look, we have applied the eigenvalue equation. But also we know that because we have this complex conjugate, so we know that psi n a psi n star is going to be equal to a n star psi n star, which in this case is going to be psi n. Remember now that we said that A is equal to a dagger. So we know that this psi n a psi n star is equal to psi n a psi n. So let's come back and we're going to say that this guy, which is psi n a psi n, is going to be equal, because a dagger is equal to a. So if I write a dagger, or if I write a, is going to be the same, is going to be equal to a n star psi n. But we know as well from the very first equation that we had, namely, if you look, this one, that this guy is equal to a n psi n psi n. So the only way that this thing can hold is if a n is equal to a n star. So meaning that the eigenvalues are real. One thing that I would really like to call your attention, because you look at these and you have seen this a long time and it looks quite cast in stone, is that hermiticity is a sufficient but is not a necessary condition for real eigenvalues, which means that a Hermitian Hamiltonian has real eigenvalues, but if the Hamiltonian's eigenvalues are real, it may be a non-Hermitian or it may be Hermitian. So the arrow goes just one way. Okay, and this is an important point because there are people researching non-Hermitian Hamiltonian systems with real eigenvalues. Now, we're going to talk about something else, but which is related to measurement and is a very important property, especially if we're talking about Hermitian operators. And this is what we call spectral decomposition. And spectral decomposition states that any Hermitian operator can be written as H sum from J equals from J equals to 1 to D, lambda J, psi J. So what you have here is you have an equation where you are pretty much stating that these Hamiltonians can be diagonalized, and this is going to be associated with the possible values of a measurement. So lambda j, in fact, are the eigenvalues of H corresponding to the eigenstates psi j. Psi j are the eigenstates of H, this operator, and D, this is the dimension of the space in which H, which is this Hermitian operator, acts. So what we are saying here is that this operator can be diagonalized. So this is the main statement. So key idea is that Hermitian operators can be diagonalized. Now note as well that since these phi j, these eigenstates, since they form an orthonormal basis, there exists a unitary operator U, which maps that basis onto, let me see, it's not, that maps that basis onto another basis set. So pretty much what we have here is we have, first, we're saying, if you have a Hamiltonian, this Hamiltonian can be diagonalized, which makes total sense because this is like, if you think about a matrix, if you have a Hermitian matrix, you can diagonalize that matrix. So it's pretty much the same principle. Then you are forming an orthonormal basis, psi A, or psi I in this case. So this means that there exists a unitary operator U, which maps that basis onto another basis set. And we can call this basis set here EJ, which is something we have seen in our last lecture when we're talking about basis changes and the properties of unitary operators, which are very important also in quantum mechanics, that you can write psi j as U EJ, where this is an unitary operator that you can use to change the basis. So this is one basis set, this is another basis set, and you can achieve basis transformation by changing the operator. And one thing that we can see also is how in this case U would transform and how in this case H, which is your Hamiltonian, would transform. This is something that is important to us because we have seen, okay, we have a Hamiltonian that can be diagonalized. Here you write this in terms of these operators here, which are composed by the eigenstates of H. You have these corresponding eigenvalues lambda j. And if you have a basis set, why not go and do a spanning using another basis set? So we can have a look. So if we start from this Hamiltonian, so let's write H is equal to j equals 1 to d lambda j psi j psi j, and we know now how they should transform, right? So we know this guy is u ej, whereby ej is the other basis set, and this is corresponding bra, so this is going to be ej u dagger, which means then that H can be written as sum from j equals 1 to d lambda j u ej bra u dagger, or even more, if you can pull these unitary operators out, and you're going to have sum from j equals 1 to d lambda j ei u here ej better u dagger. So this leads you to conclude that H is u d u dagger. So if you see, I called this guy here d, and I'm saying that I can use this to diagonalize my Hamiltonian. So in practice, this if I assume D is a diagonal matrix, that's what I can do to go from one basis set to the other. And the eigenstate, the eigenvalues are not going to change, right? Pay attention to this. You see that the lambda j are the same. And this is something you expect. If you change the basis of an operator, their eigenvalues are going to remain the same. It has to be like this. So you can clearly see here, I transform this guy, and I'm imposing that I'm transforming this such that this is a diagonal matrix, and still I can write this in terms of these eigenvalues. Okay, so all good so far. And what do I do if the eigenvalues are degenerate? Well, let's get an example, okay? Very simple one, so that we get a feeling. Let's write H as lambda 1, and then you have this projector here. Plus lambda 2, you project onto this phi 2, and you have again lambda 2, but you have another eigenstates associated with it, this psi 3. So the situation that we have is we have this lambda 1, and here we have a projector onto the subspace spanned by phi 1. Then we have lambda 2, but this lambda 2 is degenerate because it is relating to this eigenstate phi 2. So this is a projector onto the subspace. And this is related to also this phi 3. Can you see? So what is that we should do? And if you think about it, let me write it more explicitly. We have then the situation that, just for clarity, okay, lambda 2 is degenerate, and we can write H as lambda 1 P1 plus lambda 2 P2, whereby P1 projects onto the subspace spanned by phi 1, meaning that P1 is equal to this guy. So here we're using the definition of projector that we have already seen. And P2, as defined above, is going to project onto the subspace. Now pay attention because it's going to be a bit different. You're going to have a subspace which is spanned by two eigenvectors. So they are spanned by phi 2 and phi 3. So this projector looks a bit different. It looks like P2 Can you actually see the difference? What you pretty much have now is you have projector that is spanned by two of our eigenstates, and it gives you one eigenvalue, and before you have one which is spanned by just one. So you see that you can write your operator like this. So this means that any vector in this subspace, which is defined by this projector, by this later projector, any vector in this subspace is going to return is an eigenvector of H with eigenvalue lambda 2. So this is something that is quite interesting because you can actually see that this is going to behave in quite a different way than what we're used to, and we are going to come back to these when we deal with measurement. So this is going to be important. When dealing with measurement. And we're going to stop right now. And our next lecture is going to be related to time evolution operator and how we define time evolution, which is the other postulate which we have seen at the very beginning of our course. I hope you're enjoying this.